Welcome soil conservation and management students to our lecture series on soil erosion. This lecture series was initially developed for students at the Royal University of Agriculture in Phnom Penh, Cambodia as part of our session 13 lecture from our soil conservation and management course. I am Dr. Jared D. Williams from Brigham Young University, Idaho in the United States. And this particular video lecture is the fifth video lecture and is based on soil erosion and erodibility on resilience or soil erosion. So how does soil erosion and erodibility influence or is influenced by soil resilience? Okay, and again, this is video lecture number 5. And let's move my picture down here where it's out of the way. Now, soil erosion and soil resilience. So, soil erosion, when it can occur, is definitely going to reduce soil resilience. And the reason for that is it's starting to remove some of the topsoil. It's removing that topsoil, and as a result of removing some of that topsoil, we're going to have less of it. And so the ability for the soil to recover and to bounce back is reduced. So worldwide erosion rates are estimated at 7%, or we're losing 7% of our soil. Okay, and so and when we think about that number, topsoil is regenerated at somewhere between 0.003 and 0.01 centimeter per year. In other words, less than a millimeter of soil is formed per year. And so if we have this event where we lose 1 or 2 centimeters of soil, it's going to take hundreds of years for that soil to be replaced. And that's why when we were talking previously about time and the soil forming process of time, that it is a real challenge, right? And our soil additions are typically not going to be greater than our soil losses. Okay? And so as far as soil erosion goes, it really does cause a problem with our soils, and especially reduces the resilience of that soil, because we're losing the topsoil. We're losing the part of the soil that is or allows the soil to be resilient. Okay? And so, again, let me move my picture out of here. So when we think about soil resilience and erodibility, we want to think about some soil physical properties and those soil physical and how they are altered. So highly resistant soils, or soils that can bounce back from erosion, are going to be those with low soil bulk density. Now that makes sense because low soil bulk density means high organic matter, okay, high soil organic matter, and it also means that we have good structure, okay, good soil structure, porosity, and so and that goes with the ability of having more stable aggregates. Okay, we have higher available water and higher water retention in these soils, which are all really a result of this component right here, soil organic matter. So some examples here, we have some resilience practices. In other words, we're letting those soils bounce back, recover. In this scenario, we have a 2-year, and then in this one, a 6-year resilience, where we're allowing natural vegetation to grow on the soil. And so we can see here with water stable aggregates, so this aggregate stability here, and infiltration, right, so our high water available and retention kind of tied into that component, right? We look at those and you can see before following, maybe the best way is saying immediately following our disturbance and our degradation, we had aggregate stability of 44% and 13 centimeters per hour of infiltration. When after 2 years of natural vegetation, the resilience of that soil, allowing that soil to bounce back, improved our water aggregate stability to 66%, and a huge, large increase in our infiltration rate at 32 centimeters per hour. Look at our bulk density after 6 years of natural vegetation. It has, before it was 1.4, it's decreased down to 1.2, again indicative of higher organic matter. and penetration resistance, the ability for this. It's really a measurement of soil tilt, but look how well the soil has recovered with pores and tilt, and as penetration resistance has been decreased. Really, that's again ties back to density as well. In other words, soils can recover if we can put them back into natural vegetation and allow these physical properties to improve. Okay. Also, what about our chemical and biological processes? And these, again, tie back to that time concept. You notice that I have time over here. And so fast rates of microbial biomass help restore soil structure and water infiltration rates because of the additions of organic matter. Total carbon and nitrogen concentrations will promote faster microbial decomposition rates, and therefore more organic matter to build up and help start building soil aggregates. But they take time, and that's the important part, is they do take time to do that. And so you can see in the first 0 to 15 years, you have rapid recovery, right? This rapid recovery in this 0 to 15 years standpoint. Total recovery of total carbon, though, can take, to get clear out here, it's going to take 100 to 150 years. Okay, as we discussed earlier, it's very slow. And a good data point here is at 59 years, a study of total carbon and nitrogen showed us, so somewhere here on the graph, showed us that we had 71 to 85% recovery. And just to, so in 59 years we're here, but to get all the way up here, it could be another 50 to 100 years. Okay, so it's a slow process, and we have to realize that. But it takes time for soils to recover, and that rate of recovery is going to be based on soil resilience. Okay, it's the soil more resilient. Also, I want to talk about not just erosion, but what about when we use agricultural chemicals? What's the influence of those agricultural chemicals? Now, again, when we introduce an agricultural chemical, a herbicide, a pesticide, that causes disturbance. But does that disturbance result in soil degradation? And that's, again, dependent on soil resilience. If the soil is resilient, it can adapt to that degradation and recover quickly. And most agricultural chemicals are designed to decompose rapidly in soils, and so healthy soils will be able to decompose or bounce back from the agricultural chemical use more rapidly than those with low soil resilience. Okay. Now, when we look at adding agricultural chemicals, there are two approaches to how we manage those systems. One is through what we call extraction or in situ, where we actually extract the soil, run it through some processes to reclaim it, and then replace it. And we do that by extracting it or by digging it up, fixing it, and putting it right back, what we call in situ. Those processes are for severe chemical contamination. We're going to focus more on the self-recovery type of practice, and that's where we have soil resilience, and the soil can rebound or bounce back by us just letting it be, by just letting it go back to, by not interacting with it. And so, again, the way to think about that, this is allowing the macro and microorganisms, the healthy soil, to transform those toxic chemicals over time into compounds or break them down so they're not a problem. And some examples in agriculture of that is when we allow those microbe populations that are healthy and diverse, the key is diverse, to be able to break those down. So again, if we're maintaining a resilient soil, a healthy horizon with healthy microbes, it's resilient. Those microbes, part of that population, will be able to decompose and break down those chemicals. Okay? As well as if we have high organic matter, that organic matter will absorb those chemicals and make them inert and allow them then to be substrate for soil microbes. Okay? Also, the organic matter provides substrate to give the soil microbes energy to break down agricultural chemicals. Okay, that wraps up our fifth part of our Session 13 lecture series on soil resilience.